Thanks, Anand, and thanks to the Maths Club for having me here. So let me begin by saying what this subject is not. Okay. So there's a funny story behind that. When we say coding theory, this is a theory of error correcting codes, and it has nothing to do with coding as in computer programming. So I will tell you what this coding theory is. So the funny thing is that once a fifth year student approached me, ending fourth year for the fifth year project. And I spent 45 minutes explaining a tentative project involving elliptic curves and coding theory. At the end of 45 minutes, the student asked, "What do I have to code?" so, so tell me that. And then I said nothing. So then he didn't show his face after that. Okay. There's one more such funny story I will tell you about. So here is the basic setup. So you have an abstract communication channel. It can take various forms, and some data is being transmitted and some noise is entering. And you have a receiver who's getting corrupted data. So before we go into the mathematics, I will just tell you what are these things used for. Certainly there are many interesting mathematical problems here. That's what I'm going to be talking about. There are other communities, computer scientists and engineers who also work on this area, but we are approaching this from a combinatorics point of view. Okay, but before delving into that, I should tell you what is the setup, what are these things used for. So for example, this is the standard setup of a communication channel. I'll give you some examples. So you have, say, Mars orbiter mission, Mars orbiter or Chandrayaan. Deep space communication. What is happening? Say Mars orbiter. From near Mars, it is capturing data, maybe photographs or results of some experiments, and it is transmitting that data. What is the communication channel here? It is the outer space, and all sorts of noise enters. You have no control over it. The receiving station at the Earth will get completely useless data, and all the money that you have spent will be totally gone waste. You can't afford that. So therefore, you cannot afford to send whatever data you have collected. You can't send the data as it is. Otherwise, the whole mission will be unsuccessful, right? Can't afford to send the data as it is. Another example is you have a compact disk. Data has been etched onto it, but you can't etch you have digital data. You can't etch the data as it is. Why? Because there is noise in the form of dust, finger marks, which will definitely corrupt. It's very sensitive. It will corrupt the data. So you don't etch your actual data on the disk. For example, if you break your CD into 5 parts, each part will have the whole data. Okay. Similarly, there is data coming from the mobile tower to your actual handset. There's a lot of noise coming. So you can't afford. So bottom line is, cannot afford to transmit raw data. So you use what is this? That is where these things come up, error correcting codes. You don't transmit the data, you use error correcting code. So what is the idea? So let's go back to this last example. Suppose there is a lot of noise in the signal you're getting on your mobile phone. Okay. So what does the other person do? Or what do you do? One simple thing is, I cannot hear you. Can you please repeat? You repeat the same thing twice or thrice. Then you're able to get the message across. Yes? So what you have done is you have put redundancy into the data. Instead of transmitting what you wanted to transmit, you have put some extra useless stuff. which is not useful. You don't want to transmit that, but you're putting it in anyway. Basic idea. Add redundancy. Before transmitting. Okay, so just the most naive example of adding redundancy is repeating yourself 3 times, 4 times, so the message gets across even in the presence of noise. If there's, suppose I want to reach you, there's a lot of noise. If I repeat myself twice or thrice, chances are you will get the message. So, but how do you make this efficient is the question. If I keep on repeating myself, yeah, I will get the message across, but it's very inefficient. Okay, it's very inefficient. You have to, for example, in this setup, it needs to be fast. What the transmission. So this whole theory is about how to use redundancy in order to achieve error correction. So, for example, you may have seen ISBN code. Yeah, that is all. There is a redundancy. The last digit actually depends on the previous digit, or simply the ASCII code. You have an 8-digit binary string. There also the last digit is redundant. It depends on the previous 7 entries. And why is it there? It's called a parity check bit or something. So this is redundancy in order to correct errors. So let me give you the mathematical framework. Yes.
So in the first diagram, so if before the receiver you had put a repeater to amplify the lost signals, still you will get the same result that all data is not transmitted.
No, I repeat from this end. Yes. The same data I repeat.
No,
twice.
Repeater would mean amplify the lost signals which were transmitted.
No, I don't know what is lost. It is just being corrupted. Okay. Yeah, just look at the basic idea without going into the details. So that reminds me of another funny incident. Let me put down something and I will tell you. Finite. So what is the data you are transmitting? I will assume it is of a particular type, digital data, alphabet finite. Say examples are f is equal to maybe just the uppercase alphabets, or it could be the binary alphabet, or it could be ternary alphabet. And what you're transmitting is words of length n over f. What do I mean? Simply elements of f to the n. Cartesian product of f with itself n times. What does an element of this Cartesian product look like? Just an n tuple x1 up to xn, where each xi is, yeah, for example, this is just a n letter word from your uppercase alphabet. So this is our space. So I will just use some geometric notation in analogy with r to the n, Cartesian product. I'm going to just schematically think of this set of words as f to the n as a space. Okay, point here, a word I'm going to represent by a dot. Okay. So, how do you measure that a word that you sent has got corrupted? So assume what you're transmitting is words of length n from your alphabet. So you need a notion of a distance. So you send this and it went somewhere else, it got corrupted. So how do you measure the distance between two words? So here is this first definition. This is my space. I hope the space is clear to everybody. For example, if this is f and this is n is 8, you're looking at bytes. Yeah, a word of length 8 in 0 and 1 is called a byte, for example. So Hamming metric is you take two words. When I say x, I mean x1 up to xn. When I say y, I mean y1 up to yn is equal to number of I such that xi not equal to yi. Is it? Can everybody read that? The back. So you take two words and just compare in the n coordinates. In how many of these n coordinates do x and y differ? So in set notation, it is the number of i's between 1 and n such that xi is not equal to yi. That is the distance between x and y. That's clear. Some of you may have seen that a metric needs to satisfy some properties. It should be greater than equal to 0, and in fact it should be it should be equal to 0 only if x is equal to y. That is the case here. But the most important property which makes a metric useful is so-called triangle inequality. dxy is less than equal to dxz plus dzy. Okay. So this property one can check that this metric that we have defined does indeed satisfy the triangle inequality. So it's an honest metric. This is the metric which we use in most common metric that we use in information theory. Okay, so let us quickly come to how does redundancy help me to achieve error correction. So what you have is you want to transmit some information, and maybe your information was, so your information doesn't necessarily look like words of length n from your alphabet, but what you will transmit is, so let me draw a picture again. You transmit a bunch of whatever data you want to transmit is in the form of some subset called a code. C is a subset of f to the n. These are the words which you actually end up transmitting. Okay. So I will give you some examples. So the size of C, by the way, the size of this alphabet is often denoted by Q. Q is some integer. Okay. Many times it's a prime power for reasons I will tell you later, but it doesn't have to be a prime power. For example, it could be 26 here. So the size, okay, you can give a name to this. The size of this set is a subset of f to the n. Let us call it m. So these are these m words which are called code words. This is what you transmit, and when you transmit this particular thing, because of the noise, it will get corrupted to some neighboring spot. Okay. Maybe you intended to transmit this and it came here instead. You'd have no control over it, just like this outer space example. So how do you, having received the corrupted data, how do you recover? This is correcting errors. How do you recover the actual message which was transmitted? So here is, I will tell you what is happening, idea. So let us define, so for this subset C, so if you have a metric space and a subset, it becomes a metric space in its own right, or without talking in technical terms, let me just define DC is equal to a minimum of d of x comma y, where x not equal to y in C. You have a sub, so in pictures, just draw these pairwise chords. How many are there? If you have m dots here, there are m choose two such pairs. Look at the distance between them, and it will be a positive number, positive integer. Look at the minimum. It's called the minimum distance of the code. Minimum distance of C. Okay. Now, let us draw. Now, if you have a metric space, you can talk about, what can you talk about? Balls. Uh, let me say Br of x is equal to all y such that dxy is less than equal to r. Just like in Euclidean space, we can talk about this, right? This is the center of the ball, this is the radius. You can do this over any metric space. Okay, so let me draw those balls here. You have these m dots, make them the center of balls of some radius. Which radius I will tell you. Radius of the balls is dc minus 1, something, yeah, half. Roughly speaking, half of dc minus 1. What is d? Let me repeat again. The smallest of these chord lengths. Do you have any guess about what is the main property of such balls? They are disjoint. And why they are disjoint? It is because of this triangle inequality. That is where the metric property comes in. If suppose these two balls had an intersection, since this radius is less than half of d minus 1, this radius is less than half of d minus 1, triangle inequality would imply that the distance between these two ball centers, if they had an intersection, would be less than or equal to d minus 1, which is not the case. Why? Because any two ball centers are at least this dc apart. Okay, this is the main idea. So what does it tell me? Yeah, this dc is the minimum of these lengths. Okay, so my ball radius is less than half of d minus 1. So there can never be an overlap between these balls, thanks to triangle inequality and the definition of this dc. So what does it mean? Coming back to the physical picture, it means that during transmission, if the number of errors, what is an error? Some bit changing to some other bit of the alphabet, some letter in some coordinate changing to some other letter in the alphabet. If the number of errors which have happened is less than or equal to how much? This much. Then what will happen? This thing will end up, you intended to transmit this, and the corrupted word will still be in this ball only. And since the balls are disjoint, you are able to recover what was originally transmitted. Is that clear? Suppose that the number of errors, let me repeat, what is an error? Suppose this first x1 changes to x1 dash, different from x1, and everything else is the same. It means one error took place. Okay, how many coordinates got corrupted? If that number of coordinates which got corrupted is less than d minus 1 over 2, it means that your corrupted word still lands in the same ball as the ball center. So you achieve error correction. This is the main idea. Okay, so having spent this, so okay, so I said I will tell you something. So I was trying to give a similar talk. I gave a similar talk at some other institute, and I was talking about this deep space application. And one student said that this noise is actually some alien trying to contact us, so we should not be trying to correct the error. And that person heckled me, and my talk was derailed right then and there. I never quite recovered, but this audience is better. So yeah, we are not talking about such things. So okay, let's come back. So what is a good code? So we have seen how codes help us to correct errors, but okay, so so as I said, if the number of errors is half of d minus 1, then you can have error-free communication. So d over n is a fraction between 0 and 1. This is a measure of my goodness of the code. I will call it error correcting capacity. Simply speaking, how good this code is. But what is the cost you pay? Okay. So, for example, you wanted to transmit m words and you are using words of length n. Log q, log of m to the base q is roughly speaking the number of bits of information that you actually want to transmit. Okay. N bits is what you are using to transmit. Okay. This number m is how much? M is a subset of q to the n. So this is also a number between 0 and 1. And this is my efficiency or rate of transmission. Rate of transmission. Okay. This is when you want to talk about the size of a subset, we have say, okay, the size is capital M, but you can also talk about everything to the base. Take, yeah, q to the watt power equals m. Okay, you are taking a, when you take this capital M and take log to the base q, you are saying it has so many query bits of data. Okay. So this is also a measure of the size. So what do you want? You want your transmission to be efficient. So if you repeat yourself many times, yeah, you are getting error correction, but you are being very inefficient. On the other hand, if you make this 1, that means you are not doing any redundancy at all. Then what happens? Okay, you are very efficient, but you can't get error correction. So having both these numbers high is having the requirement of having both these numbers high is conflicting requirement there, conflicting goals. Okay, but that's what we want. So then the problem is we want to capture the trade-off. How to make sure that this is also high, this is also high. That's a central problem in coding theory. So I will switch gears now, but let me just put down one definition here. AQND, okay, is max mod C such that C is subset of f to the n and dc is greater than equal to d. So among all codes, all subsets of f to the n whose minimum distance is at least d, you want to maximize the size. So I fixed some ratio here and give me the maximum value here. So without the log, it is just this m. You want to maximize this. So you want this much error correcting capacity. Tell me what is the largest efficiency that you can give me. Roughly speaking, that is what this thing is capturing. Okay. So finding the values of this is a hard problem because there's combinatorial explosion going on. You simply can't, if n is large, you simply can't get your hands on this. So we will come back to this. Okay. So what are the, so I have told you the basic setup. Now, the way we, at least I approach this subject is from the point of view of a problem solving mathematician. So what is a problem solving mathematician? So I am referring to, so some of you may have read this paper by Gowers. Let me erase this part of the board. Two cultures of mathematics. So what are the two cultures of mathematics? So maybe somebody has told you this. This is not about, so maybe you can say two cultures of pure mathematics if you want. It's not about pure and applied. Okay, it's something different. What does a mathematician do? What's his job? Yeah, you have heard this. it has been told to you that you have to prove theorems. Okay, and but that's not the full story. That's one culture of mathematics. There's another culture of mathematics, and so it's important to put this thing because only one culture is being uh, introduced to you. What is the other culture? No. There are two cultures of mathematics. Okay, there is oversimplification, but still. So, what does a mathematician do, or what's the main job? Somebody said you prove theorems. Okay, but there's another culture, which is to solve problems. I'm not talking about real world problems or something. There are interesting, hard, unsolved problems, and your work is guided by those, as opposed to just learning and building on theory. Okay, these are not mutually disjoint activities. Okay, another statement that has been made: when you get into serious mathematics, you write papers which run into 200 pages. Not true. It may be true for whoever is speaking that. Okay, but there is an interesting problem which people have been trying to solve, have not been able to solve. Suppose I solve it in 30 pages. Suppose you solve it in 200 pages, which is better. The shorter paper is better. So there is the length of a paper, or whether it has high sounding words, is not always a indicator of the depth or importance of that piece of mathematics. Okay. So there is this problem solving. So that means like your work is guided by some problems which define. These are the problems which people have not been able to solve. These are interesting, and we should be solving them. So this is what guides some mathematicians. So I will talk about three problems. This has a combinatorics flavor, primarily combinatorics, primarily algebra / geometry, and this is analytical. Okay. So coming back, does a problem solver doesn't need theory? May need theory, but what is the main tool that a problem solver has? It's the nose. He has a nose, he or she. So if at some point thinking about the problem, the mathematician will himself, herself get to know that there should be a certain theory which applies here. How would it be if you start, okay, here is some theory which I'm now going to learn, and I will prove some theorem in it, which probably I and some other handful of persons may understand. Versus I'm trying to solve some problem and I anticipate that there should be a theorem or a theory of this type. Okay, so a problem solver can also, problem solver also needs theory, but when the problem solver needs it, at that point, they go to the theory and they anticipate that there's some such thing should be there, like that. Okay, so that was just a digression, but I will talk about these problems. Any questions before I move ahead? No, there is no line. It's an oversimplification. So I can't answer those questions because this is a example where it's stated as a problem, but then so problem solving typically implies that so the known theoretical tools are probably not going to yield? You need some clever solution. You need some out of the box thinking. And going through all the theory may not necessarily help you solve a particular problem. This is what is typically combinatorics problems, but it can be applied to other parts of mathematics also. It's the attitude which I'm talking about. It's an attitude. Suppose you're trying to, in your own field, you may be trying to, instead of focusing on some important problem that your theory can do, suppose you start writing 200-page theorems, papers, you might lose the chance to have a good paper in some good journal. You may be asked to write a book instead. Okay, so it's the attitude. So it's not always true that a mathematician has to prove theorems. You have to solve interesting problems also. There are both kinds. Okay, so I'm not saying this is good, this is bad, but both exist is the only point which I'm trying to reiterate of made by this. So let me come back to this. Uh, so we talked about these balls. What's the size of this ball? Can somebody tell me? Okay, whatever the size is, let me just write that. Size, as in actual set size of a ball of radius r. Radius. We can actually give a nice combinatorial formula for it. So let me put something here. Can you fill the RHS of this inequality for me? No, I didn't. Go back to this code. It has size m. There are these m balls. The size of each ball is this much. Size of a ball of radius d minus 1 over 2. This is less than equal to what? Yes, because this is a disjoint union of balls, so it's a subset of the ambient space. The ambient space has size q to the n. So it's a perfect code. C is called perfect if equality holds. Okay, that means the whole space is decomposed, partitioned into some number of balls. So very interesting question. People started asking, do perfect codes exist? There are some trivial examples of perfect codes. For example, you take this C to be all of the ambient space and this D to be zero, this thing will be 0. So there are some trivial examples, so non-trivial examples of perfect codes. People started asking these questions and they found, okay, if Q is a prime power, if this alphabet size, what is Q? The alphabet size, if it is a prime power. So I will tell you some theorem here. So let me call this number E. What E is the radius of these balls? Now what are we looking at it? We are looking at partitioning the ambient space into some number of balls of radius E, disjoint balls which actually end up covering the whole space. Then E error correcting codes, E or E perfect codes. So E is equal to 1 for all prime power alphabet. You can find perfect codes. If E is 2, there is only one example called the ternary Golay code. There is so-called binary Golay code. I can give more information about it, but so for example, this is, so I will just give one example. For example, this ternary Golay code satisfies n is equal to 11 and m is equal to 3 power 6. But let's not get into the details. So it was a major theorem proved by some Finnish. So this was a line of inquiry which several people started asking. What is the classification of perfect codes? If let's start with q prime power. Okay, so it's common in coding theory circles to say that this problem was finished with a double N in 1973 by some Finnish mathematicians. So it's often said because they put an end. So it was a major result that apart from these three, this is one code, this is one code, this is a family of codes. So this family is interesting. So I will tell you quickly about that. Just this one. But what's a, so this is, but before going there, let me, I said I will talk about some problems. So what is a problem remaining here? So if Q is not a prime power, what happens is an obvious question. And there is a theorem. If Q is composite, and E greater than 2, then there do not exist non-trivial perfect codes. So E is the radius of these balls into which you are partitioning your space for any n if the alphabet size is composite. So this theorem is not due to one person. It's the culmination of maybe 5 or 6 PhD theses. So 5 or 6 PhD theses combined give this theorem. So what is a problem which is left? Classification of double error correcting codes, and is hard. And this has been called hopeless by one of the Finnish mathematicians who did that thing. So Van Lint is one of those mathematicians. There is a graduate text in mathematics called Coding Theory. So, so with some of my BSMS students, I have worked on this particular problem, and we were able to recover some results which have already occurred, which have already appeared in literature. We haven't been able to come up with new results, but there's always room if we keep trying. That's the nature of research. And also, you don't always work on super hard problems which people haven't been able to solve. Yeah, those are there at the background, but you break it up. There are smaller cases, or there are, so in the problem solving mathematicians thinking, there is always this line of thought going back to Polya. If there is a problem which you cannot solve, you're stuck on it, you as in everybody, and what then what? There must be a smaller version of that problem, a simpler version of that problem, which you also cannot solve, and which probably holds the key. Find it. That was what Polya said. How to Solve It is a book that he wrote, and so you can find it there. Okay, so there are always such problems which students, PhD students, fifth-year students can work on. It's risky to directly work on very big unsolved problems for your career. So, so then let me come to this other topic quickly. So so we have this alphabet of size q. The actual what is it as a set doesn't matter, because our metric is saying two n-tuples, the distance between them is number of coordinates in which they differ. So the actual set, what it looks like, doesn't matter. So it's if I find it useful, I may assume that my alphabet is integers mod q. What is this? Yeah, so integers mod q. So you have remainder 0 up to q minus 1, and q goes back to 0. Okay. So advantage of this is that what is the distance between two n-tuples? You simply subtract now, because you can subtract here. So it's just a notational convenience. So you have two n-tuples x and y, subtract them and see how many zeros there are. That's the how many non-zeros there are. That's the distance between two n-tuples. Okay. So let me go back to this picture. You have f to the n, and you have some. Again, you have some a subset of size m, C subset m, and you have this DC. What was that? The minimum of these pairwise lengths. And what I do is in a metric space, given a set, you can talk about the diameter of that set. What's the diameter of a set? Yeah, it's the max of dxy, where x comma y belongs to S. This is the diameter of a set S. So take a set of diameter d minus 1, at most d minus 1, and make sure that the all 0 word belongs to S. Okay, and then what you do is you translate this. So this is your S, and you have this picture again. I'm just redrawing it. Move it to translate it to each of these. You had a subset C, right? Yeah, just do. So what is this? So if this was X, then this thing is X plus S. If this is Y, this thing is Y plus S. I again claim there is no intersection between these two, because this set, it had the all 0 word, and its diameter is at most d minus 1. So suppose two of these intersected, then what does it mean? X plus A is equal to Y plus B. A and B are in S. So then X minus Y is equal to B minus A. What is the distance between X and Y? At least D. And what is the distance between B and A? It's at most the diameter of S, which is D minus 1. Okay. So this is a generalization of the previous. For example, this could have been a ball of radius d minus 1 over 2. That would be a set of diameter d minus 1. So, but I don't want to go back to the ball. So here is what I'm taking. So take S to be 0 power n minus d plus 1 cross f to the d minus 1. So you are looking at all words whose first n minus d plus 1 coordinates are 0, and the last d minus 1 coordinates are arbitrary. Okay, it's a flat, so to speak. This has diameter d minus 1. Yeah. Because if you take two words, the first entries are just same, and they may differ. You can find two strings which are different in each coordinate, like that. Okay, yeah. So and then what can you say? I go back to the same thing. M times the size of S is less than equal to q to the n. Again, once again, because they're the same argument. So that what does that tell me? What is the size of this set? Q power d minus 1. m less than equal to q power n minus d plus 1. So MDS codes, without going into what this acronym is, equality is attained in this. Okay. So let me make it more interesting. So far we have been looking at the alphabet being of size some q, which is a natural number. Now we will jump to the case of linear codes. So your F is a finite field. Okay. For example, there is a finite field with 4 elements and it does not look like 0, 1, 2, 3 with 4 being 0. It's different. Okay. So I will no longer think of my alphabet as being Z mod QZ because this is already FQ. And so FQ to the n, words of length n, I interpret as vectors in this. Just like you have R to the n, you have some other field. And this subset of C, this subset C, I now take it to be a linear subspace. Linear subspace. It's called a linear code. And say k dimensional. So the size m which we were talking about will be q power k. So now we can start. Now probably you appreciate why we were talking about log of the size to the base q. It will be k. Okay, like that. It's the dimension. What's the advantage of a linear code? You can look at a matrix G whose rows, so we are writing words horizontally, okay? So you can look at a matrix of size k by n whose k rows form a basis for this subspace. If you have a k dimensional space, you can find a basis. And every word here looks like a linear combination. So that means the row space. If you look at the row space of this matrix, it is your code, okay? So in your actual CD business, they use this Reed-Solomon codes, which are, I will tell you how they look like quickly. Reed-Solomon codes are saying, so the data that you want to transmit is k dimensional. So fq to the k. This is what you want to transmit, but you are actually transmitting. So if you want to transmit a0 up to ak minus 1, what you do is you pick some n points distinct in your field and you cook up this polynomial a0 plus a1x plus ak minus 1 x to the k minus 1. Instead of transmitting a0 up to ak minus 1, take these to be the coefficients of a polynomial, call it f of x, and transmit fx1 up to fxn. These x1 up to xn are fixed. Okay, so how do you encode this in terms of matrices? You look at this van der Monde matrix. Is that clear? If you take this to be a row vector, what will be the output? The output will be this polynomial evaluated x1, this polynomial evaluated xn. Okay, so coming back, this is an MDS code. What do I mean by that? I mean m, the size of the code, q power k is equal to q power n minus d plus 1. That means d is equal to n minus k plus 1. How do you check that? Suppose d is always less than equal to n minus k plus 1. So if d was smaller, say d was n minus k, what does that mean? There is a code word which has, so in a linear code, instead of comparing, suppose you want the distance between x and y. X minus y is also, because you are in a linear code, x minus y is also in the code. So the distance between x and y is the same as the distance between the origin and the x minus y. So the minimum distance of a linear code is simply look at all your words and look at how many non-zero entries are there and minimize it. Minimize the number of non-zero entries in all your in the subspace, the row space of your matrix. Okay. So let me cut it short. So if you have a k by n matrix, then its row space is an MDS code if and only if all its k by k minors are non-zero. What does that mean? You pick any k columns and they are linearly independent. Okay. Is that clear? So let us, in the interest of time, let us change the question to this. Look at k by n matrices over a finite field. I will make it a little bit more precise. So let's assume k less than q, q is odd. Okay. Can you actually find k by n matrices such that any k columns are linearly independent? Is the question. Famous conjecture is that if n greater than q plus 1, there does not exist such matrices. With all k cross k minus non-zero. Why is it a conjecture? Nobody has been able to prove it, and nobody has been able to find a counterexample to date. If q is even, there are some well-known counterexamples, and there's a generalization of this theorem. So what is the let me tell you again. Not only this van der Monde type. Okay, for a van der Monde, you probably know every k by k minor is non-zero because yeah, you may have seen it in a course in linear algebra. But so if you have a k by n matrix and n exceeds q plus 1, q is odd, k is less than q, you can't have all k by k minors being non-zero. So this is a famous problem in this area, which I have been working on. And as going back to Polya, there's a simpler problem. So I will give you you have to pick n distinct points. Your finite field has size q, so there are q points. I wrote them. Turns out you can add one more, so-called infinite column. All zeros except last entry is 1. So this is a matrix of size k cross q plus 1, which you can check all k by k minors of this matrix are non-zero. So here is a basic question which people have not been able to answer. Can you put one more column here, a q plus 2th column, such that every k by k minor of this augmented matrix still remains non-zero? If you believe the big conjecture, then the answer is no. But people have not been able to even solve this. Say roughly speaking, if q is less than half of q, then people have been able to show that no such augmentation is possible. But for k greater than half the size of the alphabet, roughly, it's still open. Okay. This is a problem on which I have made progress, and there are such simpler problems which can be worked on. Okay. So, and this has ties to algebraic geometry because this is the set of points of so-called degree k, k minus 1 rational normal curve in projective space. In the last 5 minutes, I will talk about so this relates to algebra, geometry, algebraic geometry. The perfect codes business is combinatorics and whatever else you may need. Differential equations, we have used differential equations, elementary number theory, because there's anyway talk about composite numbers, prime powers. So, but the flavor is still combinatorial. So the third is analytical. So recall, so We are looking at subsets of f to the n, whose called codes, whose this minimum distance is at least d, and we are maximizing this because the understanding is what is the maximum possible. So let me put it down: log q aq nd over n. You want to maximize, yeah. So if you replace this with m, this is the largest possible m. This is the largest possible efficiency. It's a number between 0 and 1, which you can achieve for a code of inside f to the n of minimum distance at least t. So it's hard, as I said, it's very hard to get these numbers. So what's an asymptotic version of this problem? So this, let us say d is equal to some ratio. D over n is a ratio, call it x. X is between 0 and 1. Okay. And now you let n go to infinity, so you have control. But you don't know if it converges, so you take a lim sup as n goes to infinity, and you get, so this is a number between 0 and 1, so you get a function alpha of x. So you can talk, and x is between 0 and 1, so you can talk about the graph of this function on the unit square. Famous number theorist Yuri Manin showed that this function is continuous. It's decreasing. It becomes 0 at 1 minus 1 over q. People don't know the exact value of this function. People don't know if it is differentiable. People don't know if it is convex. So there's a major part of research is find good bounds on it. There are some upper bounds known. There are some lower bounds known. Trying to improve the bounds on this asymptotic information rate function. This is an analytic flavor to this problem. And all the bounds are in terms of this entropy function. So I will tell you what is this entropy function. Roughly speaking, you take I talked about a ball of radius r. Suppose the radius of the ball is x times n, where x is some ratio. You divide by n, lim as n goes to infinity. This is almost true, but I don't have time to fix this thing. So okay, this is true if 0 less than x less than 1 minus 1 over q. Here is the precise version. What does this thing entropy function look like? You may have seen it in physics. If q is equal to 2, hqx, h2x simply looks like minus x log x plus 1 minus x log 1 minus x. Okay. So you can guess what sort of a turn this problems take. Information theory, entropy, analysis is this function. So what I have been focusing on is the question of this unknown function, is it convex? Trying to gather evidence that this function is convex. Okay. Or at least suppose I fix one endpoint to be this and take the other endpoint variable. Does this secant line always stay above the graph? Convexity means secant line always stays above the graph. So if you fix one for every pair of endpoints, I'm asking, suppose you fix one endpoint. So I gathered evidence, I conjectured that this will be the case, and I gathered evidence for it. Okay. So these are the kinds of problems, major problems, but there are always a simpler version of problems for students to work on. Okay. So with that, I will stop my talk here. Thank you. Questions?
So we'd like to thank Professor Kaipa for the talk. If there are any questions, you may address them to the speaker.
This conjecture, MDS conjecture, and these goes back to an algebraic geometer Italian Beniamino Segre, before coding theory. So there are connections to even before coding theory was born. Obviously, problems have existed. They take various forms in different other areas of mathematics.